In this video, we're going to look at the geometric transforms processor in RAMP. So the geometric transforms processor allows you to do things to the geometry of a raster. The first few methods in here are basically resampling methods. So you can downsample a raster, as in reduce its resolution. You can upsample a raster, i.e. increase the number of pixels, not necessarily the resolution, however. You can clip a raster, so basically take one large raster and take a section out of it, specifying the spatial bounds. You could clip it, specifying the bounds of another raster. Or you could tile the raster, so split a raster dataset into a number of smaller tiles. So, for example, for perhaps ease of handling, that sort of thing. And the last one is to flip a raster. So you could flip it around about its rows or columns or X and Y axes as well. And there's a number of cases where you want to do that. Some rasters are encoded in a certain way that they appear flipped when you actually try to read them. So we'll have a look at each of these tools in processor methods in this video. So in RAMP, I've already loaded a synthetic aperture radar dataset of some coastline and some nearshore seas here. And what I'm going to do is I'm going to show you how the upsampling and downsampling of this works using the geometric transform method. So let's downsample this first. The cell size of the input raster, I believe, is, let's check here, I believe it's 1 by 1. Cell size is 1. So let's downsample it to say 10. So it's going to create pixels that are 10 by 10. And we'll ask it to use a kernel size, in this case of, let's say, let's use a 9 by 9 kernel. We need to be sensitive about how much we're reducing the raster in terms of its size by balancing the outputs, the ratio of the original input cell size and the output cell size with the kernel that's used on the original input raster. So there's no point, say, using a 3 by 3 kernel when we want to reduce a raster from a 1 meter resolution to a 100 meter resolution. That would just give you horrible results. So you want to use something that is roughly the same dimensions as what you're outputting. So a 9 by 9 is pretty close. A 9 by 9 on a 1 meter data set is pretty close to a 10 meter cell size. Here I can also select how I want the downsampling to work. I could take the nearest neighbor and use that value, or I could use a Gaussian kernel for my 9 by 9 kernel and use the resultant value of the Gaussian kernel. I'm just going to use mean. Let's have a look what this looks like. Okay, you can see that my resolution has been definitely reduced, and in my about data I now have a cell size of 10. It's obviously using a different color palette, but nonetheless. Let's try to upsample this data set now and see what that looks like. So back to geometric transforms, interpolated resampling upsample. I'm going to take the one I downsampled and upsample it back to 1 meter again. And I'm going to use this, in this case, a bilinear interpolation method. So let's have a look how that looks. Okay, so from my original, you can see that by downsampling it, let's set the same rendering for all of these, shall we? So let's go here. This is an EQ, so on a grayscale. So let's do a grayscale EQ. Grayscale equalized. And we'll do the same here. So here's my original, and you can see that it's quite noisy, particularly in the coastal area. And this is my downsampled version. I can start to see the pixels there, and I've upsampled it again. And although there's more pixels, there's not any more real data in there. It just has a higher resolution. What's interesting is to look at how the histograms have changed for these. So if I start with the original, this was the original histogram. My resampling of it has made my histogram look somewhat like this. So let's look at the minimum values, 5 to 279. Now I have 29.5 to 140. And when I upsample it again, I've got 30 to 136. So you do see, and you can see here how much smoother in my re-upsampled image, how much smoother the histogram is compared to say the downsampled version, and then particularly the original version of it. So that's upsampling and downsampling. Let's look at the next methods in the tool, or the processor, I should say. I'm going to skip over the clip rasters to other extents. I think this is fairly intuitive as to what these are and how they work. Essentially, you specify the bounding coordinates, and it will extract that area from the input raster and create a new output raster. And the same with clip to the extent of another raster. It's fairly intuitive as to what that means. So we'll look at tiling next. Let's just clear the rasters in here and put a new raster in that we can do the tiling on. So just wait for that whilst I do that. So to look at the next tool, I've imported some more synthetic aperture radar data, and I've extracted a little portion of it and smoothed it, despeckled it. So we're going to use the tile method, and I'm going to choose the last raster that I created, raster number 2, and I'm going to ask it to tile it into 2 by 2 tiles, so 4 tiles. The options that I have are to either create new files, raster files, or to output those to a particular location and format. I'm going to choose not to create one, so that will return the rasters into the RAMP graphical user interface. So I'll click OK, and we'll see what tiling does. Essentially, it's going to break down the raster into 4 different tiles so that it could be easier to handle for me. So here are the tiles, and I'm going to render each one of them. So it's broken this input raster down into 4 evenly spaced tiles that are now easier for me to handle and process and work with. The last tool that we're going to, the last processor method that we're going to look at is the flip raster. So I'm going to choose one of the tiles that I just created, maybe the last one, and I'm going to choose to flip it vertically. Let's see what that does. Okay, here's my original, and here's my flipped version. And as I mentioned before, this is useful because sometimes rasters are provided in a certain order where they are not necessarily the same order that you'd expect to be able to visualize the data in. So they might be acquired from the bottom up or the top down, and therefore they appear flipped. This is particularly common with satellite data. Let's take the last one that we created and flip it horizontally now, but not vertically. And let's have a look what that looks like. Okay, so this is now a horizontally flipped raster from the original version. So this has now been flipped both horizontally and vertically. So that's a quick introduction to the geometric transforms processor and the various methods that are in there. I hope this has been of use to you.